In mathematical analysis, the maxima and minima of a function, known collectively as extrema, are the largest and smallest value of the function, either within a given range or on the entire domain of a function. Pierre de Fermat was one of the first mathematicians to propose a general technique, adequality, for finding the maxima and minima of functions. As defined in set theory, the maximum and minimum of a set are the greatest and least elements in the set, respectively. Unbounded infinite sets, such as the set of real numbers, have no minimum or maximum. Definition: a real-valued function f defined on a domain X has a global maximum point at X if f for all x in X. Similarly, the function has a global minimum point at X if f for all x in X. The value of the function at a maximum point is called the maximum value of the function, and the value of the function at a minimum point is called the minimum value of the function. If the domain X is a metric space, then f is said to have a local maximum point at the point X if there exists some epsilon greater than 0 such that f for all x in X within distance epsilon of X. Similarly, the function has a local minimum point at X if f for all x in X within distance epsilon of X. A similar definition can be used when X is a topological space, since the definition just given can be rephrased in terms of neighborhoods. Note that a global maximum point is always a local maximum point, and similarly for minimum points. In both the global and local cases, the concept of a strict extremum can be defined. For example, X is a strict global maximum point if, for all x in X with XX, we have f greater than f. And X is a strict local maximum point if there exists some epsilon greater than 0 such that, for all x in X within distance epsilon of X with XX, we have f greater than f. Note that a point is a strict global maximum point if and only if it is the unique global maximum point, and similarly for minimum points. A continuous real-valued function with a compact domain always has a maximum point and a minimum point. An important example is a function whose domain is a closed interval of real numbers. Finding functional maxima and minima. Finding global maxima and minima is the goal of mathematical optimization. If a function is continuous on a closed interval, then by the extreme value theorem global maxima and minima exist. Furthermore, a global maximum either must be a local maximum in the interior of the domain, or must lie on the boundary of the domain. So a method of finding a global maximum is to look at all the local maxima in the interior, and also look at the maxima of the points on the boundary, and take the largest one. Local extrema of differentiable functions can be found by Fermat's theorem, which states that they must occur at critical points. One can distinguish whether a critical point is a local maximum or local minimum by using the first derivative test, second derivative test, or higher-order derivative test, given sufficient differentiability. For any function that is defined piecewise, one finds a maximum by finding the maximum of each piece separately, and then seeing which one is largest. Examples: the function x2 has a unique global minimum at x equals 0. The function x3 has no global minima or maxima, although the first derivative is 0 at x equals 0. This is an inflection point. The function has a unique global maximum at x equals e. The function xx has a unique global maximum over the positive real numbers at x equals 1, e. The function by 3/3 minus x has first derivative x2 minus 1 and second derivative 2x. Setting the first derivative to 0 and solving for x gives stationary points at -1 and +1. From the sign of the second derivative we can see that -1 is a local maximum, and +1 is a local minimum. Note that this function has no global maximum or minimum. The function x has a global minimum at x equals 0 that cannot be found by taking derivatives, because the derivative does not exist at x equals 0. The function cos has infinitely many global maxima at 0, plus or minus 2 pi. pi, plus or minus 4 pi, and infinitely many global minima at plus or minus pi, plus or minus 3 pi. The function 2 cos minus x has infinitely many local maxima and minima, but no global maximum or minimum. The function cos x with 0.1 x 1.1 has a global maximum at x equals 0.1, a global minimum near x equals 0.3, a local maximum near x equals 0.6, and a local minimum near x equals 1.0. The function x3 plus 3 by 2 minus 2x plus 1 defined over the closed interval minus 4, 2 has a local maximum at x equals minus 1 minus square root 15 thirds, a local minimum at x equals minus 1 plus square root 15 thirds, a global maximum at x equals 2 and a global minimum at x equals minus 4. Functions of more than one variable. For functions of more than one variable, similar conditions apply. For example, in the figure at the right, the necessary conditions for a local maximum are similar to those of a function with only one variable. The first partial derivatives is to z are 0 at the maximum. The second partial derivatives are negative. These are only necessary, not sufficient, conditions for a local maximum because of the possibility of a saddle point. For use of these conditions to solve for a maximum, the function z must also be differentiable throughout. The second partial derivative test can help classify the point as a relative maximum or relative minimum. In contrast, there are substantial differences between functions of one variable and functions of more than one variable in the identification of global extrema. For example, if a bounded differentiable function f defined on a closed interval in the real line has a single critical point, which is a local minimum, then it is also a global minimum. In two and more dimensions, this argument fails, as the function shows. Its only critical point is at, which is a local minimum with f equals 0. However, it cannot be a global one, because f equals minus 5, maxima or minima of a functional. If the domain of a function for which an extremum is to be found consists itself of functions, i.e., if an extremum is to be found of a functional, the extremum is found using the calculus of variations in relation to sets. Maxima and minima can also be defined for sets. In general, if an ordered set S has a greatest element M, M is a maximal element. Furthermore, if S is a subset of an ordered set T and M is the greatest element of S with respect to order induced by T, M is a least upper bound of S in T. The similar result holds for least element, minimal element and greatest lower bound. In the case of a general partial order, the least element should not be confused with a minimal element. Likewise, a greatest element of a partially ordered set is an upper bound of the set which is contained within the set, whereas a maximal element M of opposite A is an element of A such that if M be then M equals B. Any least element or greatest element of opposite is unique, but opposite can have several minimal or maximal elements. If opposite has more than one maximal element, then these elements will not be mutually comparable. In a totally ordered set, or chain, all elements are mutually comparable. So such a set can have at most one minimal element and at most one maximal element. Then, due to mutual comparability, the minimal element will also be the least element and the maximal element will also be the greatest element. Thus in a totally ordered set we can simply use the terms minimum and maximum. If a chain is finite then it will always have a maximum and a minimum. If a chain is infinite then it need not have a maximum or a minimum. For example, the set of natural numbers has no maximum, though it has a minimum. If an infinite chain S is bounded, then the closure CL of the set occasionally has a minimum and a maximum. In such case they are called the greatest lower bound and the least upper bound of the set S, respectively.